Review of voltage distribution on metal oxide surge arrestor and suggestions for improvement in high voltage applications. Problem statement. Aim of this paper is to collect and consolidate all the works related to voltage distribution of metal oxide surge arrestor. This paper may be helpful for any researcher to do further research with a good start. Voltage level of power network is increasing and hence voltage rating of MOSFETs are also increasing. Because of this, height of MOSFETs and hence stray capacitance are more. So remedial measures must be considered for good operation of MOSFET. An important requirement is successful conduction of MOSFET under very fast transients. Hence further research is essential on this. Contributions. This review paper presents a summary of research conducted by various researchers on voltage distribution of MOSFET from the year 1970. The study is done on both non-conduction and conduction modes of MOSFET. This paper shows computation of stray capacitance and its ill effects. A case study is taken and analyzed for both the modes. Suggestions are given for achieving more uniform voltage distribution and reducing response delay of MOSFETs. This is the dimension of single stack MOSFET for 66 kV arrestor and arrestor blocks also seen. Ill effects of stray capacitance. Distribution of stray capacitance affects behavior of MOSFET during non-conduction and conduction modes, making more non-uniform voltage distribution. Discs at the top are subjected to a higher voltage stresses and hence high thermal stresses, which leads to a faster thermal aging of these highly stressed discs and hence lifetime of arrestors is reduced. Voltage non-uniformity during conduction mode is also more significant when steepness of current surges increase. There is a delay in operation of MOSFET, especially under very fast transients. Stray capacitance is increased with the height of MOSFET. Stray capacitance is increased with the height of arrestor. This is given in the table. And the diagram shows non-uniformity in the voltage distribution for different heights of MOSFET. For conduction mode, the voltage distribution is shown. Voltage distribution without grading ring, with one grading ring and with two grading rings are present. Conduction mode, voltage distribution is given for different current surges. Current surge of 8 by 20 microsecond, 10 kiloampere, and current surge of 5 nanosecond front time and tail time 10 microsecond, 10 kiloampere magnitude. Conduction mode, for current surge 8 by 20 microsecond 10 kiloampere, arrestor is conducting successfully. For current surge of 5 nanosecond bar 10 microsecond and 10 kiloampere magnitude, there is a delay in response in arrestor. The voltage appeared across the top stack of arrestor is 215 kV for front time of 1 microsecond current surge and 219.2 kV for 5 nanosecond front time current surge. Now the voltage is reduced to 213.8 when grading rings are placed. Shortening of MOSFET with a high gradient material. Stray capacitance is reduced. Voltage distribution is made more uniform in both non-conduction and conduction modes. Time lag between residual voltage and discharge current is minimized. Hence MOSFET conducts successfully. MOSFET with high voltage gradient material plus rare earth additives shortens length of arrestor. Process of preparing genetically modified arrestor, powder weighing, ball milling, calcination and sieving, hydraulic press, sintering, grinding, electrode plating, arrestor block. Further research. Stray capacitance reduction is achieved by using new dimension of grading rings and different composition of materials. This is achieved by modifying basic composition of arrestor material with a suitable manufacturing process. Rare earth elements are very suitable for obtaining required higher voltage gradient arrestor, hence height of arrestor is reduced. One of the best suited rare earth material is scandium oxide, which enhances grain boundaries and increases possibility of formation of high voltage gradient material for arrestor. It is suggested that new materials like scandium oxide may be used for further reduction of height of arrestor. This holds good for polluted MOSFETs also. Conclusions. From literature, it is found that voltage distribution is non-uniform across MOSFET due to presence of stray capacitance. Stray capacitance increases with the height and hence voltage rating of MUSA. One of the popular Elmil measures is number, size and location of grading rings. These are studied with a case study of 198 kV MUSA. The remedial measures may not be sufficient to reduce the non-uniformity, hence new material composition may be used. Preparation of new high-gain arrestor material, that is scandium oxide, would be a suitable method for achieving reduced height. Placing capacitive voltage transformer and short relay cable in the system are more suitable for making more uniform voltage distribution only for conduction mode. These are all the selected references. Thank you.